Welcome back, and now here we go, section 11.4. So we have been in the probability chapter. I know it's been a while since we've seen each other. So remind me, when I'm calculating the probability of something, okay, what is the ratio that we create? So if I ask you, for instance, what's the probability I roll a 4 when I roll a die? How do I do that? Okay, that's part of it. So that's going to be my denominator, the total number of outcomes. So my total is the denominator. What do I put in the top when I'm calculating probability? I'm sorry? The event, the successes. Yes. So for rolling a 4 on a die, it would be 1 chance out of 6. Okay, so probability is successes divided by total. Okay, and we'll have a couple probability problems today, so we'll get to review that. Then the second section, we talked about something called odds. Odds is another way to look at the likelihood of something happening, but instead of successes divided by total, like probability is, odds are either odds against or odds in favor. Odds against changes the ratio to failures divided by successes. Okay, it's a different ratio, no longer the total. And then odds in favor are successes over failures. Okay, again, no longer the total. It gets completely split apart. Then we talked about expected value in section 11.3. Expected value gives us the long-term average if you do something repeatedly. And the way you calculate expected value is it's the probability of an event times the net amount. Now I got a couple people said they had some questions about that. So if we have some time at the end of today, then we'll go back and we'll review a couple expected value problems to make sure that we're all feeling as decent as we can about that. But in the meantime, now we're going to talk about tree diagrams. So all the probability we have done so far has been the probability of what's called a simple event. Okay, one thing happening and there's been no complications. And so what we're going to build up to now, starting with this section right here, is the idea of what's called a compound event. What happens when we have more than one thing, or what happens when there's a decision that I have to make between two things? And so we're going to work up to being able to calculate probabilities of compound events. So where we're going to start in section 11.4 is what's called the counting principle. I didn't leave a blank here because there wasn't really a good place for me to leave a blank. But here's what the counting principle says, and we're going to use the counting principle now pretty much for the rest of the chapter. What the counting principle says is if a first experiment has m distinct outcomes. Okay, so this letter m right here, all that is it's a number. So when I roll a die, that's going to be 6. Okay, when I pull a card out of a deck of cards, that's going to be 52. Okay, that's what's happening. So if I can do a first experiment in m distinct ways, and a second experiment can happen in n distinct ways. Again, that n is just a number. Then if I do these two experiments at the same time, if I do them together, then the number of distinct outcomes is m times n. Okay, that's how we would see how many possible things that can happen. Well, that's a complicated thing, so let's go ahead and do an example. So example 1. How many possible outcomes are there when I flip a coin? Okay, so I'm keeping this nice and simple, numbers nice and low. When a coin is flipped and a die is rolled. Well, in and of themselves, how many outcomes are there? How many possible things can happen when I flip a coin? Okay, 2. How many possible things can happen when I roll a die? 6. Perfect. So the number of possible things that can happen if I on this table up here, if I flip the coin and roll a die, the total number of things that could happen are 2 times 6, or there are 12 outcomes. That's what the counting principle tells us. So I didn't type this on. I probably, if I retype these in the future, I'll put this question on. But here's what I would like you to do for me. I would like you to tell me how many outcomes are possible when you roll 2 die, which I guess would be dice. When you roll 2 dice. So just take a moment, scribble down what your thoughts on that are. And if you're right, great. And if you're not, then we're going to learn. No problem. Okay, how many outcomes are possible with the first die? 6, great, times. How many outcomes are possible with the second die? 6. So that means when you roll two dice, when you're playing Monopoly, okay, there are 6 times 6 or 36 possible outcomes that can happen. Now, the counting principle just doesn't apply when you do 2 things. It applies no matter how many things you do. So for instance, again, I wasn't thinking ahead too great when I made the worksheet, so I apologize. Just going to go up to the top where there's a little room. I want you, again, you're going to hypothesize here your answer to this. How many things can happen? So how many outcomes when you roll, this time, 3 dice? So if you're playing some sort of board game that has 3 dice, how many possibilities are there? So take a moment, see what you think that's going to be. Okay, so here's what the counting principle says, and you're just applying it every time. You already told me the answer to this question. There's 6 possible outcomes with the first die. Then how many outcomes with the second? 6. How many outcomes with the third? 6. Okay, so 6 times 6 times 6. Did anyone do that? 216. Thank you. So there's 216 possible things that can happen. Okay, so that's what the counting principle is. We're going to practice that a few more times. So going down to example 2. My big purpose in example 2, well, there's 2. First purpose is we got to practice the counting principle a few more times. My second purpose with this is to introduce you to these 2 words, which will become part of our lexicon as we're going through and talking about probability. What happens if I'm going to do something with replacement and do something without replacement? So those 2 things mean something different. So the situation here in example 2 is 2 cards are drawn from a standard 52 card deck. Okay, so you're out somewhere, somebody holds a deck of cards in your face and says, pick a card, and you pull one out. And then we're going to do this experiment 2 ways. What do we do with that first card? What we do with it affects the probability of the next thing that happens. Okay, so we're going to do this with replacement. We're going to do this without replacement. So we're going to determine the number of possible outcomes if I draw these 2 cards with replacement or without. So with replacement, you help me out. You've pulled the first card out of the deck. You've seen that whatever it is, that's a 2 of diamonds. If we're doing this experiment with replacement, what do you think you're going to do with that card? You're going to put it back in the deck. Okay. With replacement means you put it back in and it can be used again. Okay. So when we go to do it without replacement, I pick the first card. I look at what it is. What do you think I'm going to do with it then if I'm doing this without replacement? You're going to keep it. You're going to throw it away, put it in your pocket, whatever you're going to do with it. But you do not put it back in the deck. Okay, that's the difference. All right. Well, if we do this with replacement, how many cards are possible with my first draw? There's 52 cards in the deck, so 52 times. Now I'm pulling it out. I'm noticing what it is, but then I'm doing this with replacement. So now how many cards how many options are possible with my second draw? 52, right? It doesn't change, right? Because it's the same 52 cards because I put that first one back in. Does that make sense? Do you understand what the words with replacement are telling us? Okay, so then 52 times 52, and I pop that in the old calculator. It's something large. 52 times 52 is 2704. Well, we're going to do the same problem here, but this time we're doing it without replacement. So I'll answer the first part. When I first put the deck of cards in your face, you have 52 options for how many cards you can draw the deck. But this time, whatever card you're looking at, you put it in your back pocket. How many cards are now available for the second choice? 51, yes, so it changes. So my number of options becomes different this time now that I'm doing it without replacement. Now there are 2,652 options. So once again, this is my First time doing all these worksheets, so I didn't necessarily put all the problems I should have. So here's what I would like you to do. I want you to redo parts A and part B, but this time, instead of drawing 2 cards out of the deck, I want you to draw 3 cards. And I want you to tell me how many options are possible when I draw 3 cards, first with replacement, and then secondly, without replacement. Bless you. All right, so doing this with replacement, we're going to draw 3 cards. So let's just go through it. How many options are available when I draw the first card? 52. I replace that. How many options are available with the second card? Yes. Okay. Sorry for the boring question. I replace that. How many cards are possible with the third card? Yes, there you go. 52 each time because I'm doing it with replacement. And so when I do that, what'd you get? I'm sure you've already done this. How many options are possible? 140,608. Do I have confirmation of that? Yeah, sounds right to me. That's great. Thank you very much. All right, this time we're going to do it without replacement. We're just applying the counting principle. So the first card, you have 52 options. And then how many options for the second card now? 51. Okay, now that card we take out. We're not replacing it. So how many options for the third card? 50. If we were drawing 4 cards, okay, I'm not going to write it down, but if we were, how many options would be left for the fourth card? And etc. You just keep doing the same thing depending on how many cards you were choosing. So 52 times 51 times 50, when I multiply those together, how many options total? 132, 600. Do I have confirmation on that? Awesome. Thank you. Sounds so good. Are we doing all right? Do we see what the counting principle is telling us is going on? Okay, excellent. Remember, if you have any question, please ask it. I'm here all day. We got plenty of time. So now what we're going to do is we're going to extend the counting principle. We're going to say, okay, if I want to know what those outcomes are, okay, what I can do is I can have a process to figure that out. Now, I'm not going to apply this process for decks of cards with 52 options. That would be math torture, and that's not what I'm here for. But we can use this in smaller cases. So what we can do is we can create what's called a tree diagram. And a tree diagram is just a tool. Okay, it's not anything really too complicated, although I'm going to walk around and because sometimes students, as you're getting to know how to do this, have some misconceptions. But when we want to list all the distinct outcomes of an experiment, a tree diagram is the tool that we can use. So for instance, example 3, this one's the one I'm going to do. I'm going to use a tree diagram to list all possible outcomes of flipping 2 coins. Okay, so we're going to flip 2 coins, the simplest experiment I could possibly think of. Okay, so we're going to flip 2 coins. Okay, so I flip a coin. What are the possible outcomes when I flip the first coin? Heads or tails. So here's how you draw a tree diagram. Now I know trees tend to grow upward, and you can draw your tree diagram upward. Just for space sake, I'm going to go side to side here. So here's my seed. So my tree is growing out of the side of a mountain. Okay, and what you do now is for each event, you create a branch. So when I flip the first coin, what I have is I can have a heads H, or I can have a tails T. So that's my first coin. Those are the possible outcomes that I have. You with me so far? Okay. Now that's not much of a tree. That's like a twig so far. So now what we're going to do is we're going to flip the second coin. Now notice I've got two ways that I could go. So first, I'm going to cover up the bottom. Let's pretend on the counter when I flipped, I've got a heads facing up. And now I go to flip a second coin. What are the possible options when I flip my second coin? Heads or tails. So now what I'm going to do, growing out, this is the result of the first coin. Now growing out of that, I'm going to do a heads or a tails. Same thing can happen when I cover up the top. Let's just say laying on the table is tails up. Well, if the first coin has the tails, what are the possible options when I flip the second coin? Heads or tails again. So again, this tails, this is the result of the first coin. And now with the second coin, I can have heads or tails. Now, if my example had been, we're going to flip 3 coins, then I would go and do the whole thing again. I would say, okay, I got a heads with the first one and a heads with the second one, and then I could have a heads or a tails. So you would just keep adding more branches depending on how many times you're performing whatever event. But we're done here. So there's my tree. And what my tree now allows me to do in a nice, quick, clean way, so that I know I have all the options, is I now get to be a squirrel and I get to run on the branches. Okay, so I'm going to list all the possible outcomes. When you're asked to list all the possible outcomes, what you're creating is what's called the sample space. Okay, so just in case you see those words bantered about, sample space just means you're listing all the possible things. And so here we go. I'm going to put a set squiggle. Okay, and so I'm just a squirrel. So I'm following the branches. I'm doing this in no particular order. I'm just starting up top. Heads and heads is the first possible thing that could happen. Heads and tails, second possible thing. I'm done with the top branches, so now I'll go to the bottom branches, tails, then heads. And then finally, tails and tails. Now, I understand flipping 2 coins, you didn't need a tree diagram for that. You could have probably thought that through and come up with all the options. But my point is, with this first simple example, is this is a tool to help us when things get more complicated. Okay. Did you have a question, or are you just stretching out? Okay, great. So here's what I would like you to do, and I'm gonna pause the video. So if you're watching on the video, just pause on your end too. I want you in example 4 to make your attempt to draw a tree diagram, and here's what's happening. The first thing you're doing is you're flipping a coin. So your first pair of branches is going to look just like my first pair of branches, but then instead of flipping a coin the second time, you're going to roll a die. So what we're doing is we're going to list out the things that can happen that we saw up here in example 1. There should be 12 possible things, and now we are going to list out those 12 things. So draw your tree and then list out the sample space, and I'm going to walk around and help clear up any problems there might be. All right, great job, everybody. So just in case you're watching on the video, here's how it looks. So the first event is flipping a coin. So we have a heads and a tails that are possible when we do that. And then we roll a die. So if I have a heads laying up on the desk, then I have 6 possible options. 1, 2, 3, 4, 5, 6. If I have a tails facing up, so it looks like a palm tree. So there's my tree diagram. And then the sample space, again, I'm just a squirrel. And so I've got, using the top branch, no particular reason for doing that. I've got heads and 1, and then heads and 2, heads and 3. These are all the possible options that I can get when I flip a coin, and then I roll a die. So I appreciate your patience and letting me run around to the class, because I think this is a fairly simple, now remember, simple doesn't mean easy, simple means not super complicated. I think it's a relatively simple thing, but it's easy to have some perception errors. And I like to be able to just go around and fix those so that we can do those better. We good up to this point? Everybody feeling all right? All right, then we're gonna flip the page. We're gonna continue. So here's example 5. I'm gonna work example 5, and then your example 6 is gonna be very similar to this. So example 5, it says, a radio station has 2 tickets to give away for Monster Jam. And why wouldn't you want to go to Monster Jam? There are 4 finalists for these tickets. Okay, so these are just names of some friends of mine. So that's, if you get to be a friend of mine, you get to be an example. So the names of the finalists are Christine and Mike and Larry and Phyllis. Okay. So here's what we're going to do. We're going to determine the number of points in the sample space, meaning what are all the possible ways that I can draw two names out of a hat. And then we're going to construct a tree diagram. And then we're going to determine a couple of probabilities. So we'll get to review that from what we talked about earlier. All right. So when I draw two names out of the hat for these Monster Jam tickets, whoever's name I draw out first, am I putting their name back in the hat? No, they can't win twice. Okay, so no one's winning twice. So this is a without replacement problem. So here we go. When I put my hand in the hat, there we go. It's been a long spring break. When I put my hand in the hat, how many possible names can I draw out for the first ticket? 4. Okay. There's 4 people that could win the first ticket. And so whoever wins that first ticket, they're now celebrating on the sideline because they can't wait to go to Monster Jam. And now I put my hand in the hat the second time. How many options are there for the second ticket? 3. Okay, great. So there are 12 possible outcomes that can happen when I am giving away these tickets. Okay. So far, so good. We're doing all right. Okay. Now I'm going to come out to the side here so I have enough room for my 12 possible options on my tree diagram. So I've given a letter that we can use for each of these people. So here's my seed. Here's where I'm going to start my tree. The first time I reach my hand in the hat, what are the possible outcomes that can happen? 4. What are they? C, M, L, and P. Great. Now let's be careful and remember that we're doing this without replacement, right? So if Christine wins the first time around, what are the possible options for my branches for the second time? Yep, M, L, and P. Notice Christine can't win twice. If Mike wins the first time, what are the possibilities for the second set of branches? C, L, P. Fantastic. If Larry wins, what are the options for the second ticket? C, M, P. C, M, P. You guys are doing great. Thank you for all your help. If you're not doing great, please alert me. Okay, there's nothing wrong with you. If you have a question, this can be difficult stuff, so no problem. And then if Phyllis wins, we would all say that what are the possible things that could happen? Okay, CML. Okay, so the tree diagram is just a way for me to think through all the possibilities. So now over here in the space underneath B, I'm going to list out the sample space. These are the possible arrangement of outcomes. So I could have Christine and Mike, I could have Christine and Larry, and Christine and Phyllis. Whoops, C and P. And then I could have Mike and Christine, Mike and Larry, Mike and Phyllis, and then Larry, Christine, and then Larry, Mike, and then Larry, Phyllis, and then finally Phyllis, Christine, Phyllis, Mike, Phyllis, Larry. There we go. There's my 12 outcomes. Okay, now we're going to use that sample space. Once you've got the sample space, you've done the bulk of the work. The rest of this should be nice cool down to this. We're going to determine the probability that Christine is selected. Now notice it doesn't say Christine is selected first or second. It just says what's the probability that somewhere Christine has been selected. So my probability. How many different outcomes does Christine occur in? So 1, 2, 3, 4. She happens a couple other times. 5, 6. So that's 6 out of how many total possible outcomes? 12. And I'm just going to pop that into my calculator. You can remember you can always reduce a fraction. I'm just going to put it in the calculator. 6 divided by 12 is just 0.5. Right there in the middle. Half the time Christine's going to be the winner. All right, the second one says, okay, we're going to get a little more specific. What's the probability that Christine is selected and then Mike is selected? So Christine and then Mike. And so how many times does that specific arrangement happen? Yeah, it only happens once. Okay, I'm just going to put a little check mark right there. That's the one time that it happens. So one time out of 12, that's a reduced fraction. You're welcome to leave it. But if you pop it into the calculator, remember my preference is 4 decimal places to get enough detail. I think my math lab likes 3. So I'm going to put this in the calculator, and it's 0.0833 is my result. Yes?
Does it need to be in order? Because it says Mike and Christine after.
This one says probably Christine selected and then.
Okay.
So that one, yes, the order matters. So that is a beautiful question. If I had asked the question like this, what's the probability that Christine and Mike are picked together? Okay, well then that would be 2 because we have Mike and Christine the opposite way. Okay, so that make sure you're reading what the problem's actually asking for. Okay, so take into account every detail. Great, great question. Love that question. Are there any other questions you've got? All right, so we're going to do example 6. We're going to do it twice. Okay, just to make sure we feel good about the words with replacement and without replacement. So example 6, here's what you're going to do first. You're going to go through and you're going to do the whole problem. And if you have a question, raise your hand. I'll come to you. Okay, but this first time you're going to do it with replacement. Okay, so we are picking 2 balls out of a bag, and there's 1 red, 1 blue, 1 green, 1 orange. So the first time I do this experiment, when I reach my hand in and I see what color the ball is, I'm putting that ball back in the bag. Okay, that's what with replacement means. Okay, so that affects your A part, the number of points in the sample space, and it affects your B part, the tree diagram. Okay, so I'm going to give you a couple minutes to go through as much of that problem as you can. And if you need anything from me, please wave your hand around. I'm happy to help. Let's see how you did or how you're doing. Probably not quite done, but I just want to make sure we're dispelling any problems that you have. So I'm just going to underline this. We are doing this with replacements. Okay, so this problem's a little bit different than the previous one, because in the previous one, you were drawing names out of a hat. That was the situation. So we weren't putting the name back in. Okay, so here we go. What are the number of points in the sample space? Okay, well, the first time I reach my hand into this bag, how many different options do I have?
4.
Okay, 4. Now, whatever ball I pull out, I am looking at it, I'm noting the color, I'm putting it back in. So now how many options are there for the second one?
4.
Okay, there are still 4. Okay, so that means my sample space is going to have 16. So now what we're going to do is we're going to use a tree diagram to list the options. So here's my seed. And so when I reach my hand in the first time, I could come out with a red, a blue, a green, or an orange. So far, so good. We doing all right? Anyone not doing all right? Okay, well, again, we're doing this with replacement. So when I pull the red ball out of the bag, what are the options for the second one? All the same, right? Because we replaced it. Red, blue, green, orange. If I pull the blue one out, what are the options for the second one? Perfect. Red, blue, green, orange. I got to make my branches different lengths here, and I'm going to make these ones longer. So to pull the green one out, then I think you're going to tell me that we could get the red, the blue, the green, or the orange. And then finally, if I pull the orange one out first, I can get the red, the blue, the green, and the orange. Now, when we redo this example in a few minutes, okay, the bottom part says on the back of the sheet, we're going to repeat this example, but this time we're going to do it without replacement. That one's going to look kind of like the ticket problem that we just did. All right, so now let's list that sample space. So this is going to take a minute. Sorry. This is kind of as big of a sample space as I'll probably have you do one of these, because I don't want to, again, I'm not trying to try your patience. I'm trying to teach you a little appreciation for math. That's all. So we could get red, red, and then red, blue, red, green, and red, orange. And then with the blue one, we could get blue, red, blue, 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 green, blue, orange. Then with the green one, we could get green, red, green, blue, green, 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 orange. And then last but not least, we could get orange, red, orange, blue, best combo, orange, green, and then orange, orange. There it is. Okay, so just a couple probability problems to finish this out. So the C problem says, determine the probability that the red ball is selected twice. So the probability of red, red. Well, how many times does red, red happen? Okay, 1 out of 16, great. And you can leave it like that. Reduced fractions are perfect. Or if you put it into your calculator, you got 0.0625. Okay, again, we doing all right? Determine the probability that neither ball is orange. Okay, so the probability that there is no orange. Well, how many times do I get no oranges? Okay, so I'm just going to put a check mark over them. No orange here, no orange, 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 and all the rest do. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9. Did I hear 10? I think I counted right. 1, 2, 3, 4, 5, 6. Okay, yeah. I think it's supposed to be 9. So 9 out of 16. Again, that's a reduced fraction. If you got that, great. If you put it in your calculator, 0.5625, that's going to be the 4-digit decimal. Everybody see why that's a 9 on the top? We good? Okay. The next one says, what's the probability that the orange ball is selected at least once? Okay, so the probability of at least one orange. So at least one orange means one or more. I'm going to circle these ones that have one or more. So that's 1, that's 2, that's 3, 4, 5, 6, 7. So that happens 7 out of 16 times, and that's 0.4375. All right, well, here is the last problem I have on the sheet. And then, like I said, we're if there's any questions about expectation that we did just before the break, then we can do a couple of just review examples of that. But for example 7, what I want you to do is on the back of the sheet or on another sheet of paper, repeat example, do the A, the B, and the E part. I mean, you're welcome to do all 5 parts, that's fine, but in particular, I'm interested in the A, the B, and the E part, but this time you're doing it without replacement, okay? So that's the key. We're changing that one word just to make sure that you see the difference. If anyone needs anything, just raise your hand in the air. Happy to come help out. If there's something you're not just quite seeing. All right, another minute or so, we'll get going. Okay, so this time we are pulling the 2 balls out of bag again, but this time we're doing it without replacing the first one. So first thing is how many points in the sample set space can I expect? So with the first pull, there is 4, and then how many options with the second pull?
3.
Okay. So that means that this time there's 12. This tree diagram is going to look very similar to the example 5 that we did with the tickets. That's why I had us do the other one first, just so be a little bit different and to maintain your interest a little more. So here's the tree diagram. First time I reach my hand in the bag, I can get the red or the blue or the green or the orange. So there we go. Now this time though, we got to think this through. When I pull the red ball out, what are the options for the second one? BGO, blue, green, orange. When I pull the blue one out the first time, my options are, yep, RGO. When I pull the green one out, I have RBO. And then when I pull the orange one out, I have RBG. We good? That making sense to everybody? All right, I'm happy to hear it. I hope you're being truthful with me. We're not in a rush. So I've got red, blue, red, green, red, orange, blue, red, blue, green, blue, orange, green, red, green, blue, green, orange, and then finally orange, red, orange, blue, orange, green. And there we go. So, I mean, we can do all 3 of these problems. I just had to do the last one because it's the only one that's kind of interesting. So what's the probability that a red ball is selected twice? So what's the probability of 2 red? Well, how many times does that happen? 0. So the probability is 0. And remind me, this is review. What does the probability of 0 mean about something? It's impossible. It's not going to happen. Great. So then the second one, D, says what's the probability that neither ball is orange? So the probability of no orange. Yeah, so 6 out of 12. So I'm just going to put a check mark over those just as we go through. So no orange, 1, 2, 3, 4, 5, 6. All the rest of them have it. So half the time when you do this and you pull 2 balls out of the bag, you're going to get no orange. And then last but not least, the probability that that the orange is at least once. Yep, that's the same thing. It's all the ones that I haven't checked off have at least 1 orange. So that's 6 out of 12 as well, or 0.5. All right, that's tree diagrams. That is probably associated with them.